This is our lecture on section 1.3, vector equations. I'm going to break this into three parts. The first part is some vocabulary. The second part is a problem that we work through together. And the third part is more terminology, but a very important concept. So third part, very important. So let's get started on this vocabulary from the introductory portion. A matrix that has only one column is called a column vector, or just a vector for short. So we're going to use this word vector all the time in the rest of the course. And we may, while it certainly matches up with what you have called vectors before, we are going to have our own unique way of thinking of what a vector is. R2 is a set of all column vectors with exactly two real number entries. That's the XY plane, basically, just as you have learned in previous math courses. But now notice how we designate these elements or points in R2. We write them as column vectors, 1, -3, 0, 0, 5, -6 are examples. And at the same time, we can think of them as 2-by-1 matrices. R3 is a set of all column vectors with exactly three real number entries, and R3 is basically three-dimensional space. Here are some examples written as column vectors, or you could say 3-by-1 matrices. Now, when we say Rn, we're just trying to talk about all possible dimensions at one time. In any particular example, n has to have a specific value, but sometimes we like to talk about collectively all possible dimensions, so we say Rn is a set of all column vectors with exactly n real number entries, where n is some positive integer. Could be n-dimensional space. In my examples, I have both, I have here a vector from R5, 5-dimensional space, and sometimes, again, we'll try to write down a vector that is an element of Rn. Now we don't know exactly how many entries there should be, so symbolically we'll write something like this: U1, U2, U3, ... to Un, and n-by-1 matrix in Rn. Now in this course we will not use any of the other vector notations that you may have used in Math 110C or other courses. So we will not write 2i minus 4j plus 6k if you've seen that kind of notation before. We'll just write that as a column vector, 2, -4, 6. And if you've used brackets, or if you've written vectors out horizontally with the components horizontally, we're not going to do that either. We're going to write it in a column vector form. So the vector -1, 5, which is a notation you may have used in 110C, will be written as a column vector, -1, 5, in this course. So there are two ways in which we can visualize vectors in R2. Consider 1, -3. Sometimes we will think of the point 1, -3 as representing the vector. No arrow at all. Often in higher level math we think of points in space or in the plane as vectors. Now we also can use the arrow emanating from the origin to help us visualize a vector. And we get a lot of good insights from working with arrows. So we will do that sometimes, but we also will need to just think of vectors as points in the plane at some times in the class. So just think of these as two different ways we visualize what this information, 1, -3, means as a vector in R2. And similarly with R3, here's an example, 1, 5, 6, which we can think of as just a point in three-dimensional space. And sometimes we'll think of that vector as being represented by an arrow emanating from 0, 0, 0 out to the point 1, 5, 6. Each form of visualization is useful in certain circumstances. We'll go back and forth between the two. In higher dimensions, visualization is not possible, but still we can often think analogously to lower dimensions. When mathematicians work in R4 or R5 or R6, they're really using what they know, their experiences in lower dimensions, to help them understand what's happening in higher dimensions. Notation, boldface type, is used to name vectors. When writing by hand, we will indicate boldface by writing a line over the letter. So we might write what I have here, V with a line over it is the vector 1, 5, negative 6, or W with a line over it is 0, 1, 0. Sometimes people write an arrow over the letter. I'm not going to use it, the arrow notation. Just a line over the V, line over the W is a way to indicate we have a vector that would be in boldface in our textbook. So we have vectors. We can add vectors of the same dimension. If you have the actual components, like 1, 2, 0 plus 0, 3, 6, it's easy to add. You just add across. 1 plus 0 is 1, 2 plus 3 is 5, 0 plus 6 is 6. It's interesting to note that when we use that arrow visualization in three-dimensional space, so there's an arrow corresponding to this vector u, it's actually in the xy plane, and the arrow corresponding to the vector v is actually in the yz plane. If we think of the arrow for u and v as lying on a plane, and we extend two sides parallel to v, one parallel to v, one parallel to u to form a parallelogram, a diagonal of that parallelogram in space is a representative of u plus v, this vector 1, 5, 6. So that's just an example of how useful the arrow visualization can be. We can also multiply a vector by a real number called a scalar. So here's 2 times 359. I'm saying that's 2 times the vector w. And when you multiply by a scalar, each component gets multiplied by the scalar. So the 2w becomes 6, 10, 18. Again, in space, if we use arrows to visualize, there's a nice picture here because I've drawn w emanating from the origin. 2w is going to lie on the same line and extend twice as long. 3w would be 3 times as long. Negative w would point in the opposite direction. Negative 3w would be 3 times as long, pointing in the opposite direction. Now here's something that's probably new for everybody, I would think. We can form what's called linear combinations of vectors of the same dimension. Linear combination is going to be probably one of the most important concepts in this whole course that we'll use all the way through. So let's go ahead and define it. If v1, v2 to vn are vectors of the same dimension, and if s1, s2 to sn are scalars, that means real numbers, then if we take s1 times v1 plus s2 times v2 plus all the way down the line till we get to the last one, Sn times Vn, that is called a linear combination of the vectors v1, v2 to vn with weights s1, s2 to sn. Linear combination is a pretty simple concept. There's nothing profound, hard about it, but it actually is profound, and it's going to be very helpful to us in this course. So here's an example with specific vectors. I just made this up, right? I pulled these out of the blue. v1 I'm calling 2, 1, 0. v2 is negative 1, 2, 1, v3, 4, negative 3, 1. So here's an example of a linear combination. 2v1 minus 3v2 plus a half v3. I can subtract because minus 3v2 is the same as adding a negative 3v2, right? And fractions are fine. In fact, any real number coefficient is fine there, or any real number weights, we might say. And so 2 times v1 minus 3 times v2 plus a half v3 is right here. And the calculation is very easy. And just go through the first row. Maybe 2 times 2 is 4, minus 3 times negative 1 is plus 3. 4 plus 3 is 7, plus a half times 4 is 7 plus 2 is 9. So there's the first entry. And you do the same for the second and third. So this vector on the right, 9, negative 5.5, negative 2.5, is this given linear combination of v1 and v2 and v3. So that's the end of our introduction. The next video will be a problem that we work out using this idea of linear combination.